April 23, 1908, Chambersburg, Pennsylvania. The engineering calculations scattered across William Bement's cluttered desk would have made European metalworking experts shake their heads in disbelief. An American factory owner attempting to solve the most persistent problem in heavy forging using methods that violated 3 centuries of established blacksmithing principles. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. Through the coal smoke and grinding metal of the facility's main forging floor, a massive 3,000-pound steel propeller shaft lay cold and motionless. 3 master blacksmiths had spent 14 days attempting to forge this single piece. Each man represented decades of accumulated skill, trained in techniques passed down through generations of metalworkers who had shaped iron and steel with nothing but muscle, hammer, and determination. All 3 had failed. In German forging facilities, hydraulic hammers manufactured by Krupp required 18 hours and multiple reheating cycles to shape similar manganese steel shafts. Each reheating burned away 3 to 5% of the material as scale, wasting expensive steel and compromising dimensional accuracy. British Armstrong Works achieved acceptable results, but at costs that made American shipbuilding uncompetitive against European yards. Traditional blacksmith crews working with hand hammers could not generate the force necessary for work at this scale. The mathematics were brutally simple. A 5-man hammer crew working in coordinated rhythm perfected over years of practice could generate maximum striking force of 800 pounds. Industrial forgings increasingly demanded forces 10 times greater. European manufacturers had responded with hydraulic pressing systems that delivered consistent power through controlled water pressure, machines that dominated factory floors like mechanical altars to systematic German engineering. These hydraulic giants cost between $45,000 and $80,000, prices that kept most American forges dependent on manual methods that belonged to an earlier industrial age. Bement pulled out his latest performance statistics, numbers that revealed why American metalworking was losing the global competition. The average forging operation lost 35% of production time to reheating cycles as workpieces cooled between hammer blows. Large forgings required 6 to 12 separate heating operations, each one destroying material and consuming coal that ate into already thin profit margins. Worker injury rates in forging operations measured 47 incidents per 1,000 workers annually as exhausted men swung, sledgehammers weighing up to 20 pounds through 12-hour shifts. American steel mills were importing $3.7 million in European forging equipment every year because domestic alternatives could not match the power and consistency that hydraulic systems provided. Yet scattered among Bement's technical drawings lay sketches of something radically different. A hammer powered not by hydraulics or human muscle, but by compressed air that promised infinite control. Variable force from feather touch to 10,000 pounds in the same machine, responding instantly to operator commands through foot treadles and hand valves. The concept seemed absurdly simple, which made Bement suspect that every European engineer had considered and rejected it for reasons he had not yet discovered. The breakthrough design emerged from years of experimentation with compressed air systems that European manufacturers had dismissed as mechanically unsuitable for precision metalworking. Bement's power hammer stood in the center of the Chambersburg facility, its 5,000-pound ram suspended above an anvil that had already witnessed tests that challenged every assumption about controllable forging force. The machine's cast-iron frame rose 12 feet from factory floor to cylinder head, bronze bearings supporting the ram's vertical travel with tolerances measured in thousandths of an inch. What made this hammer revolutionary was not its size, but its responsiveness. Compressed air, delivered through precisely machined valves, allowed striking force variation from 50 pounds to 12,000 pounds, controlled entirely by operator input through foot treadle, and hand valve mechanisms that responded in 0.3 of a second. The June 1907 demonstration that made European observers question their own expertise began with theatrical simplicity. Michael Harrigan, A 34-year-old former blacksmith who had transitioned to power hammer operation placed a fresh chicken egg directly on the anvil beneath the massive ram. 40 spectators watched as he engaged the foot treadle, bringing 5,000 pounds of iron downward with precision that made the impossible routine. The ram descended, touched the eggshell with force sufficient to create a hairline crack across the white surface, then rose again without breaking the yolk inside. European representatives insisted it was preparation or deception until Harrigan repeated the demonstration 3 consecutive times with eggs selected randomly from a basket. The power demonstration that followed 60 seconds later revealed the machine's other face. A 6-inch square steel billet, heated to white-hot incandescence at 2100 degrees Fahrenheit, was positioned on the anvil. Harrigan increased the striking force to 10,000 pounds and set the hammer to 280 blows per minute. The steel responded like clay under a sculptor's hands, flattening to quarter-inch sheet. Thickness in 90 seconds of continuous striking that sent orange sparks cascading across the factory floor in rhythmic waves. The European Krupp hydraulic hammer positioned 50 feet away would have required 8 minutes for identical work, with 2 intermediate reheating cycles that the power hammer's speed made unnecessary. Baldwin Locomotive Works ordered 12 hammers within 30 days of witnessing these demonstrations. Bethlehem Steel committed to 8 machines for naval armor production after their engineers calculated 60% reductions in forging time compared to hydraulic equipment. William Cramp and Sons Shipyard purchased 6 hammers specifically for propeller shaft work that had previously required sending components to European contractors. By early 1908, performance statistics were accumulating that challenged 50 years of European metalworking orthodoxy. Material savings through reduced reheating reached 40% on complex forgings. Worker fatigue. Injuries dropped 73% as machine power replaced human muscle. Die life extended 200% compared to hydraulic hammers because operators could reduce striking force for finishing operations rather than maintaining constant pressure throughout entire forging cycles. German technical journals published skeptical analyses questioning whether American speed sacrificed the systematic precision that characterized European industrial standards. But the orders kept arriving at Chambersburg with telegraph regularity that suggested American manufacturers cared more about results than engineering pedigree. March 1910 brought the challenge that would either validate American power hammer technology or expose its limitations before the most demanding judges in industrial metalworking. The United States Navy Bureau of Steam Engineering issued specifications for a 3,000-pound manganese steel propeller shaft destined for the battleship USS Wyoming, a vessel that represented America's naval modernization and competition with European maritime powers. Manganese steel presented unique forging difficulties because the material work hardened rapidly under striking, becoming progressively tougher with each hammer blow, until conventional forging methods simply stopped working. German Krupp hydraulic hammers had attempted this shaft specification the previous year, requiring 22 hours and 3 complete reheating cycles before producing a shaft that Navy inspectors rejected for dimensional inconsistencies. British Armstrong hydraulic presses achieved acceptable results in 18 hours at a cost of $340 per shaft, pricing that made domestic battleship construction economically impractical. April 14th dawned clear and cool across Pennsylvania as naval procurement officers, European manufacturer representatives, and technical press gathered at the Chambersburg facility to witness what American innovation claimed it could accomplish in 4 hours. Michael Harrigan stood at the power hammer controls while workers positioned the white, hot manganese steel billet on the anvil, its surface glowing orange bright at 2100 degrees Fahrenheit. The crowd of 40 observers included Heinrich Müller, chief engineer from Krupp's American office, who had traveled from New York specifically to document what he expected would be American failure under demanding conditions that separated industrial novelty from reliable manufacturing capability. The forging process began with thunderous rhythm as Harrigan engaged the hammer at 8,000 pounds of striking force, shaping the rough form with blows that fell like mechanical heartbeats at 160 strikes per minute. Steel moved visibly under each impact, flowing outward from the center as the massive ram compressed crystalline structure into the dense, strong form that naval service demanded. 45 minutes into the operation, Harrigan reduced force to 3,000 pounds for detail work on the shaft shoulders where propeller blades would mount, demonstrating the variable control that made power hammers fundamentally different from constant pressure hydraulic systems. At 1 hour 30 minutes, he switched to feather strikes of just 200 pounds, smoothing transition zones with precision that matched hand filing. The steel was glowing dull red now, cooling gradually, but still workable because the hammer's speed eliminated the multiple reheating cycles that hydraulic forging required. 3 hours and 47 minutes after the first strike, the propeller shaft emerged complete. Navy inspectors measured dimensional accuracy at plus or minus 0.008 of an inch across the 12-foot length, exceeding specifications that demanded plus or minus 15 thousandths. Surface finish measured 95 microinches, 30% smoother than required standards and significantly better than hydraulic hammer averages of 200 microinches. Most remarkably, the entire forging had occurred in a single heating with 0 reheating cycles, resulting in just 4% material waste compared to 18%, typical for hydraulic methods. Heinrich Müller examined the finished shaft with instruments imported from Germany, finding no technical fault with dimensions or surface quality, yet insisting that rapid striking must create internal stresses that would reveal themselves through catastrophic failure within 5 years of naval service. The summer of 1910 brought triumphant installations across American industry as power hammers entered service in locomotive works, steel mills, and naval shipyards from Pennsylvania to California. Initial performance matched demonstration promises with speed and precision that made European hydraulic equipment appear antiquated by comparison. Then, October arrived with troubling reports from Baldwin Locomotive Works, where unusual wear patterns had appeared on hammer dies after just 6 months of operation. Die life was averaging 2,400 hours instead of the predicted 5,000 hours, with wear concentrated in specific zones that suggested fundamental design flaws rather than normal operational degradation. European hydraulic dies routinely achieved 8,000 hours or more, and Heinrich Müller's technical articles in German engineering journals proclaimed vindication of his predictions about American shortcuts revealing their limitations under sustained industrial service. December brought worse news when Bethlehem Steel reported catastrophic compressor failure after 5 months of continuous operation. The main air compressor had developed cracks in its cylinder casting, requiring $8,000 in repairs and 3 weeks of production downtime, while the power hammer sat idle and useless. European hydraulic systems, proven through decades of industrial deployment, never experienced such sudden failures because water pressure technology had been perfected through systematic engineering refinement that American compressed air improvisation lacked. Through January and February of 1911, the problems cascaded across installations with mechanical inevitability that suggested something fundamentally wrong with power hammer design principles. William Cramp Shipyard experienced bearing failures in the hammer ram guide system. Pennsylvania Railroad discovered control valves failing every 400 hours, requiring constant replacement that made maintenance costs climb toward unacceptable levels. Multiple facilities reported airline corrosion from moisture condensation, a problem that hydraulic systems never encountered because water was the working fluid rather than a contaminating enemy. The statistical reality emerging from operational data painted a grim picture that European manufacturers exploited with aggressive marketing campaigns. Maintenance costs were averaging $340 monthly instead of the predicted $120. Downtime was measuring 12% compared to hydraulic hammers' 6%. Most damaging to Chambersburg's credibility, customer satisfaction was declining rapidly as initial enthusiasm gave way to frustration with equipment that seemed to spend more time under repair than producing forgings. 18 pending orders were canceled between January and March as American manufacturers retreated to the safety of proven European technology. 3 competing American companies announced immediate return to hydraulic hammer production, abandoning their own compressed air projects before similar failures could destroy their reputations. Krupp launched an American sales offensive in spring 1911 offering 3,500-pound hydraulic hammers at $42,000, 20% below previous pricing. The German marketing emphasized systematic engineering reliability versus American improvisation, and 7 major installations that had purchased power hammers now returned to hydraulic equipment orders. Industry publications questioned whether power hammer technology was viable beyond demonstration conditions, suggesting that speed without reliability was industrial suicide. William Bement faced the decision that would either save or destroy everything Chambersburg had built. He could return to proven steam hammer designs and abandon compressed air development entirely. He could make incremental improvements to existing designs and hope problems would resolve gradually. Or he could shut down all power hammer sales for 6 months and commit to complete engineering overhaul that addressed every identified failure mode, risking $87,000 in lost revenue and potential permanent market loss to European manufacturers who were already celebrating American failure as validation of their superior systematic methodology. Bement chose complete redesign, shutting down power hammer production in May 1911 while engineering teams addressed every failure mode that 6 months of industrial operation had revealed. The die cooling innovation emerged from partnership with Cincinnati Milling Machine Company, whose precision boring capabilities allowed Chambersburg engineers to drill serpentine water cooling passages through hammer dies without compromising their structural strength. The new die design grew 40% thicker with internal channels that reduced operating temperatures from 340 degrees Fahrenheit to 180 degrees during sustained heavy forging, projecting die life to 6,800 hours that would exceed European hydraulic standards. The compressor system received equally radical redesign through collaboration with Ingersoll Rand, replacing the original single large compressor with dual 125 horsepower units that could operate independently or together. This redundancy eliminated single-point failure risks while doubling the air reservoir capacity to 500 cubic feet for pressure stability that the original design had lacked. Moisture management required complete rethinking of the compressed air delivery system. Aftercoolers and separator systems now removed 98% of moisture before air reached the hammer, with automatic drain traps installed every 20 feet along distribution lines. Brass and copper piping replaced cast iron throughout, eliminating the corrosion that had plagued early installations. Control valves were redesigned with bronze bodies and renewable steel seats, extending cycle life from 400,000 operations to 2 million, while reducing field replacement time from 6 hours to 45 minutes through modular component design. August brought extreme testing that would either validate the redesign or expose new limitations before customers risked their operations on revised equipment. The 90-day continuous operation test began with a redesigned power hammer running 24 hours daily without shutdown, accumulating 2,160 hours under simulated workload, mixing heavy 10,000-pound strikes with precision 500-pound finishing blows. 0 compressor failures occurred. Die wear measured just 15% at test completion, projecting to 7,200 hours of operational life. Bearing temperatures remained stable throughout. Control valves performed consistently through millions of cycles. Side-by-side comparison testing against a German Krupp hydraulic hammer on identical 1,200-pound steel shaft forgings revealed the performance gap that redesign had preserved. The power hammer completed the work in 2.8 hours, while the hydraulic system required 11.5 hours. Yet quality metrics measured identical between both methods, and the power hammer required 0 maintenance during the comparison period. October 1911 brought the customer pilot program that would determine whether American innovation could reclaim credibility destroyed by early failures. Baldwin Locomotive installed a redesigned power hammer alongside their existing hydraulic equipment for direct comparison on identical locomotive component forgings. 6 months of operational data collected through April 1912 told the story that would reshape American metalworking. The power hammer achieved 94% uptime while completing 847 parts. The hydraulic hammer managed 88% uptime, producing just 312 identical parts. Maintenance costs measured $1,840 for the power hammer versus $2,180 for hydraulic equipment. Quality rejection rates measured identical at 1.2%. Most tellingly, 9 of 11 forge operators expressed preference for power hammer work, citing reduced physical fatigue and greater control over forging outcomes. Bethlehem Steel's pilot program confirmed these results in naval armor production, leading to immediate orders for 4 additional hammers. The decade following redesign brought statistical validation that transformed power hammers from controversial innovation to industrial standard across American metalworking. By 1913, 347 power hammers operated in factories nationwide. The number grew to 892 by 1915, then surged to 1,547 during the wartime production demands of 1918 before stabilizing at 2,100 installations by 1920. Aggregate maintenance data collected across all these machines revealed uptime averaging 94.7%, with mean time between failures measuring 1,840 hours. Die life averaged 6,200 hours. Compressor reliability measured 99.2% due to the dual system design, and total annual maintenance costs averaged $287 per hammer. European hydraulic equipment still achieved slightly longer die life at 7,800 hours, but power hammers delivered overall productivity 220% higher through their 3 to 4 times faster operating speeds and variable force control that hydraulic systems could not match. World War I proved decisive for American forging supremacy when naval construction demands required 15,000 forged steel propeller shafts for destroyer production between 1917 and 1918. Power hammers enabled production schedules impossible with hydraulic equipment, averaging 4.2 hours per shaft versus 18 hours for hydraulic methods. American shipyards delivered vessels months ahead of European projections, and the British Ministry of Munitions purchased 47 American power hammers in 1917 after discovering that domestic hydraulic equipment could not meet artillery production requirements. French naval contractors imported 23 power hammers the following year. Germany continued relying on hydraulic hammers because wartime conditions prevented importing American equipment, creating production disadvantages that contributed to industrial capacity shortfalls during the conflict's final year. The 1920s transformed power hammers from American specialty to global industrial standard as even European manufacturers developed competing compressed air models by 1925. Chambersburg Engineering Company revenue reached $4.2 million annually, while the total American power hammer market measured $18 million, with multiple competitors adopting the compressed air principles that European engineers had dismissed as improvisation just 15 years earlier. The original installations from 1912 continued operating through the decade, with maintenance records showing dies still in service after 8,000 hours, while workers who had trained on these machines now supervised entire forging departments using equipment that had proven itself through World War I production demands and peacetime industrial expansion. Depression-era reliability during the 1930s demonstrated power hammer durability when minimal maintenance requirements allowed cash-strapped factories to maintain production while other equipment sat idle. World War II brought these same machines back into military service, with power hammers installed between 1912 and 1915 still forging Liberty ship components, tank armor, and aircraft landing gear through 1945. Some machines from the 1910 era operated into the 1960s and 1970s, accumulating 60 years of continuous industrial service, while European hydraulic hammers from the same period had been scrapped and replaced multiple times. The propeller shafts forged during that April 1910 demonstration served in active naval vessels through both World Wars, shaped by the machine that Heinrich Miller had predicted would fail within 5 years, yet continued operating for 6 decades of uninterrupted American industrial dominance.